Hello, this is OCR Further Statistics. We're in Bivariate Data 2, Rank Correlation, and the first video, calculating Spearman's rank correlation coefficient. We already have a test for correlation, using Pearson's product moment correlation coefficient. But for this to be valid, there are a number of restrictions about the data. Both variables need to be random. It's no use if one of them is controlled. The data needs to be bivariate normal, at least approximately. You don't need to know what this means, just how to check for it. The scatter diagram needs to be approximately elliptical. It only works if the association is linear. But there are other forms of association, such as exponential. And you mustn't have any outliers. All of this is obviously very restricting. What if our data fails at any of these? Well, there is an alternative. It isn't a stronger test, but it has almost no restrictions, so can be used much more widely. Most importantly, we're looking to see if there is an association, not a correlation, despite the title. We're not testing a linear relationship. Rank correlation is correlation between the ranks, not the data. So we are losing information. But, as I said, we have fewer restrictions. Spearman's rank correlation coefficient is in fact Pearson's product moment correlation coefficient of the rankings, although we'll see that there is an easier way of calculating it than the usual PMCC formula. It investigates for a monotonic relationship. That means that as one variable increases, the other one increases. Not necessarily perfectly, because otherwise we would have perfect association. But it needs to be at least approximately increasing as one increases, or decreasing as the other increases. What we mustn't have is a situation where the data is clearly going down and then up again. That is not monotonic. But remember that we're not looking for a linear relationship. A hypothesis test on Spearman's rank correlation coefficient requires no modelling assumptions. This is the real strength of the method. You can use it in so many situations where you can't use PMCC. This correlation coefficient is represented by R subscript S. Obviously, ranking the whole population would not be feasible, so we work with a sample. As with PMCC, the value of RS always lies between -1 and 1. And also, corresponding with PMCC, -1 would represent perfect negative association, 0 no association, and 1 perfect positive association. Here's how it works. In this example, we're looking for an association between maximum temperature and daily turnover for a cafe. First of all, you rank the two sets of values. Make sure you rank both sets of data in the same order, or correlation will switch direction. So both lowest to highest, or both highest to lowest. If you're using a computer, which is sensible if your dataset is big enough to be meaningful, there's a rank function in spreadsheet software that you can use. In the exam, you will not get any tied rank values, although you may well want to explore how you might deal with ties. OK, now insert the rankings, not the values, into your calculator and find PMCC of these rankings in the usual way. Pause the video while you check you can remember how to do this. You should get a value of RS is equal to minus 0.6485 to 4 decimal places. Alternatively, you can calculate this by hand. This rather neat formula is much easier to use than the PMCC formula. Deriving it is not on the specification, but it's an interesting and not too difficult exercise to prove that if you are dealing with rankings from 1 to n, rather than data, the PMCC formula reduces to this. You'll need to note that you are summing a series of integers and make use of sums that you know, such as triangle numbers. This is how the formula works, which you do need to know. D is the difference between the rankings, so start by working this out for each pair. For consistency, subtract always the same way and include the negatives, although as you're squaring next, they don't matter in the end. So 4 minus 6 is 2, 9 minus 3 is 6, 8 minus 1 is 7, 3 minus 9 is minus 6, and so on. Now square these differences. So minus 2 squared is 4, 6 squared is 36, and so on. And add them up. The sum of the d squareds in this case is 272. N is 10, so substituting these into the formula, we get 1 minus 6 times 272 divided by 10 multiplied by 10 squared, which is 100, minus 1. And that comes out to be minus 0.6485 to 4 decimal places, which is of course the same as we got with the calculator. That's the end of this video on calculating Spearman's rank correlation coefficient. In the next video, we'll look at using this to conduct a hypothesis test.